recording.
You can start.
Okay, so it is my great pleasure to host and chair the session of the tutorial on formal analysis of AI-based autonomy. And this is a tutorial prepared by Hazem, Torfah, and Sanjit Seshia from UC Berkeley, Daniel Fremont from UC Santa Cruz, and Sebastian Junges from Radboud University. And this tutorial will be an extensive story about different verification-related activities that can be done around this topic, from modeling to runtime assurance, with the focus on runtime verification. So I'm looking forward to this very exciting tutorial, and this tutorial will be given by 3 out of 4 co-authors. So it will be given by Sanjit, Daniel, and Sebastian. And the floor is yours.
Okay, thank you, Dehan. Thank you to everyone who's tuning in, and thanks to the PC chairs and the organizers of the tutorial for the invitation. So I'm really excited to talk about this topic of formal analysis of artificial intelligence or AI-based autonomy. This is a topic that my group has been working on for about a decade now. And we've done many explorations in this area, all the way from modeling of systems to verification, to synthesis, to runtime assurance. And in this tutorial, we hope to give you a glimpse of some of the tools we've developed, some of the techniques we've developed, which we think are of interest to the broader community. And we would love to engage with the runtime verification community on collaborative work that uses these tools and extends them and so on. As Dehan mentioned, this is a joint tutorial with Hazem Torfah, Daniel Fremont, and Sebastian Junges. Unfortunately, Hazem was not able to join us for the presentation today, but he was very much the leader of this effort to get this tutorial presented here today. The theme, the setting here, of course, is one that we're all familiar with. It's the proliferation of artificial intelligence or AI in all aspects of our daily lives these days. So AI, broadly speaking, are computational systems that attempt to mimic aspects of human intelligence, including especially the ability to learn from experience, which is commonly referred to as machine learning. And increasingly, we're seeing AI being used in various autonomy settings where systems are either fully autonomous or semi-autonomous, working with humans, as you see in the many examples on the slide. And so in particular, a lot of these machine learning and AI components are being integrated into safety critical autonomous and semi-autonomous systems. And an excellent example of this are automotive systems, where, as you can see, there's a growing use of things like deep neural networks in various aspects of autonomy in these kinds of systems. So for self-driving cars, for example, as you can see, there's use of deep neural networks for things like object classification, detection, segmentation, and so on. But they're really used very much throughout the autonomy stack. And this use of AI and ML is only projected to grow over the next decade. At the same time, there are growing concerns about safety. We've seen in the literature numerous papers, including from the formal verification community, showing that deep neural networks can be easily fooled or produce wrong results. And unfortunately, there have been accidents, including some fatal accidents, involving potentially the failure of AI and ML-based components. So the topic that my group has been looking at for the past many years is whether we can address the design and verification challenges of AI and ML-based autonomy using formal methods. And I'm assuming this audience knows all about formal methods, so I will not give a definition here. But instead, what I'd really like to share with you before we dive into the tutorial is a view that, that we looked at over 5 years ago now on what are the challenges of applying formal methods to this domain. We characterize this theme of applying formal methods to AI-based systems as the verified AI challenge. And about 5 odd years ago, we wrote a position paper on this topic. And I'd like to share with you some of the insights that we said back then, which I think are still quite applicable today. So here's the standard view of formal verification. You have 3 inputs on the left: the system under verification S, the environment of the system, operating environment E, and the specification it has to satisfy phi. And the task in formal verification is to ask if S, when composed with E, satisfies phi. And ideally, you want a yes or no answer, right? Either it does, and ideally you want some proof, or no, it doesn't, and you want one or more counterexamples showing how things can go wrong. In AI-based autonomy, and we'll be using autonomous vehicles throughout this lecture, there are multiple challenges. And one of the first challenges is that of environment modeling. The environments in which these kinds of systems operate are very complex. Just think about the traffic environment of a self-driving car, right? You don't even have a good idea of the number and types of agents in the environment, let alone have good models of the behaviors of those agents. So that's the first challenge. How do you model the environment in a realistic way? The second challenge is just the complexity of these systems. So you have large deep neural networks with hundreds of thousands, if not millions, of parameters. And then these are really hybrid systems, right? So discrete and continuous properties of a scale that we typically are not able to handle using even the state-of-the-art hybrid systems verification methods. And then finally, the specification itself is a tricky question, because many of the uses of AI and ML are for tasks like perception, which are not easily formally specified. For example, is this the image of a car? Well, it's hard to define what exactly an image of a car is, right? And so the summary here is that even coming up with the inputs to the verification process is not easy. But if somehow we get past that hurdle, then of course we come to the key problem in formal methods that we often grapple with, which is how do you search these very high dimensional input and state spaces? And here, the problem is even exacerbated because you're dealing with high dimensional sensor data that is the input to these systems, right? Of much higher dimensionality than we are typically used to handling. And then finally, we would like to do synthesis, but the state of the art in terms of defining how to do correct by construction synthesis is still very primitive for these types of systems. So these are the sort of 5 challenge areas that we characterize in this paper. The first being environment modeling, which includes modeling human behavior. The second being formal specification. The third being how do you model and represent these learning systems. The fourth being how do you scale up verification as well as design tasks like training and testing components. And finally, how do you do design for correctness? And in that paper, in our 2016 paper, we laid down a bunch of principles which we have since revised a couple of times. In my group and in many other groups, we've been trying to address these challenges, exploring whether these principles work well. And in this tutorial, I'd like to give you a glimpse, as I said, of some of the progress. But I won't be able to cover, my presenters and I, co-presenters and I will not be able to cover all of the details. And so if you're interested in the broader verified AI agenda and things that have been done in this topic, please go to this URL, learnverify.org/verifiedai, and we have a bunch of resources and papers and so on. All right, so with that, I want to get to 2 of the open source tools that will form the basis of today's tutorial that we've been developing over the last 3 odd years. The first is Scenic, and the second is Verify. Scenic is a high-level probabilistic programming language for modeling environment scenarios for AI-based autonomy. And Verify is a back-end toolkit that goes with Scenic for requirement specification, as well as implementing a suite of algorithms for design verification, testing, and debugging of these sorts of systems. As I mentioned, they're open source tools. Here are the URLs, and you can also get it from our web pages, links from our web pages. We're really trying to develop these tools in a very collaborative fashion and work with people from academia, industry, as well as government. And we've already had many successful collaborations in this regard. Right? So if you're from industry, we hope this can help you improve the assurance of the systems you're building. If you're from academia, we would love for you to use these tools in your research. For example, the runtime verification community has done outstanding work on topics like falsification, runtime monitoring, and things like that. And we think these tools are very complementary to those topics, as we will mention during the presentation. So you can integrate your tools with these tools as well. And we've also been interacting with government and regulators to help them use these tools in evaluating the safety of these systems. So you only want to have these tools be part of the set of tools that the community uses. We can share scenarios and metrics, develop a corpus of tools and data. Okay, so if you're interested in collaboration, we would love to hear from you. All right, so with that, let's dive into the details of the tutorial. I'll start out with an overview of Scenic and Verify, just giving you a taste of the basic syntax of the Scenic language. I'll also talk a little bit about falsification and how it is implemented in the Verify toolkit. We'll do a little case study using a robotic simulator called Weedbots. Then I'll pass the baton to Daniel Fremont, who will tell you more about dynamic scenarios in Scenic, how do you model dynamics of systems, and we'll do a case study in using autonomous driving simulators, including the well-known Carla. He'll also talk about how you go from falsification to debugging to retraining neural networks. This will use a case study in the avionics explain simulator. Then Sebastian Junges will take over and talk about how you then in this pipeline go to runtime monitor generation in a data-driven fashion, again, continuing the explain case study. And then we will, at the end of that, conclude with some ongoing topics and directions for future work. Okay, and we'll stop during the presentation for Q&A at various points. But if you have questions, keep them coming on the chat or the Q&A window as appropriate. All right, so let me start out with Scenic. As I mentioned, Scenic is a probabilistic programming language defining essentially distributions of scenes or scenarios. So a scene is essentially a configuration of objects and agents in the world, right? So for something like an autonomous vehicle, it's in the 3D space that constitutes the environment. A scenario is really an evolution of scenes over time. So scenario brings in the temporal aspect. And Scenic has many use cases that we've explored and others have well, including generating synthetic data, generating test cases, doing formal or semi-formal verification, using it for debugging machine learning components, for design space exploration, and so on. Okay, so what is Scenic? Here's a very small snippet of a Scenic program. I will later on take a few minutes to go over this line by line, but the high-level view here you can see is that it's, first of all, it's a DSL. The syntax is essentially largely based on Python, but also with, you can think of it as a mix between Python and English, right? So design the language to be very readable and accessible even to people who are non-programmers or starting out as programmers. So what this scenario does is it models the static scenario of a badly parked car. And so it essentially first picks an ego object from whose viewpoint the car is being viewed. It picks a spot to place the badly parked car. It picks an angle, a bad angle to park the car at, and then it places the car, okay? And when you connect Scenic with a backend simulator or renderer, in this case, it's the Grand Theft Auto 5 rendering engine, every time you run the Scenic program, it samples from its underlying distribution and produces an image. And you have some sample images shown down there. The probabilities may not be obvious in this program, but when I go through this line by line, I'll describe to you, what exactly is going on in terms of the probabilistic sampling. So that's the static version of Scenic. We first published this work as a technical report in 2018 and later on at PLDI, and a journal paper will appear soon. Here's the same Scenic program, but now extended with dynamics. So the bottom is pretty much the same, except the ego vehicle now has an associated behavior, which I haven't shown the code for here, but it's basically driving while avoiding collision. So it's just trying to maintain lane while braking if necessary to avoid a collision. Also, the badly parked car has an associated behavior, which is called pull into road. And what it's going to do is, as the ego vehicle approaches, okay, it waits until the distance falls below 15 meters. And when the distance falls below 15 meters, it pulls into the lane of the ego vehicle and follows that lane, okay? And now if you connect this to a backend simulator, in this case, Carla, and you run the program each time, you produce a new simulation, right? So here's one example of the badly parked car pulling into the path of the ego vehicle. Here, the blue car is the ego vehicle. As it drives down this road, the badly parked red car will pull into its path, and so on, okay? So that's, as you can see, already just connecting Scenic to a backend simulator and running it allows you to generate data, right? Either static data or dynamic data. Okay. Now, Scenic, one of the advantages and reasons we wrote Scenic is because while you can do the same thing using native Python or other languages, Scenic is at a high level, making it easy to specify fairly complex scenarios with very few lines of code. Okay, so here's two examples of the static feature of Scenic. On the left, specifying platoon of cars. On the right, specifying bumper-to-bumper traffic. And you can do this in about 20 lines of Scenic code. And they're all fairly readable. Okay, so now let me walk you through the badly parked car example, line by line. To you, you know, how the syntax works and how the sampling works in a very basic way. Okay, so on the left here, I'm going to show you a schematic of the map in which the scenario is being executed, right? In Scenic, you can connect it to a map of your choice, in which it will then use as a workspace and use for scenario generation. Okay, so in Scenic, we have a number of simulators supported, about over 5 simulators supported in Scenic. And we have interfaces as have a driving library that defines basic actions and objects for the self-driving car domain. Similarly, we have a few other domains supported. So here you see a map where on the leftmost side, you have this triangle. That triangle represents a car or an object. In this case, it's an ego vehicle, which has indicated by this green circle. And now you're seeing the view cone of the ego vehicle. In this library, GTA.model, this library defines a set of objects and agents that are compatible with the GTA simulator with associated distributions. So if you say, I want the ego object itself to be a car, ego is now a random variable. Car is an object with an associated distribution. It has basically a feature vector, which is like the model of the car, the color of the car, the position of the car, the orientation of the car, all of that as part of the attribute feature vector of ego and of car. And when you write the statement, you sample from that distribution and assign a value to the ego object. Okay. Then once you've picked a position for the ego object, that defines a view cone, which is specified by these blue dashed lines. And so now, based on that view cone, you can compute a region, which is the visible curb region, right? This is the part of the curb in the road that is within the view cone of the ego vehicle. And what you want to do is pick a point with an orientation uniformly at random. So by default, these objects have default distributions. In this case, it's a default uniform random distribution. These can be changed by the programmer, of course. Okay, so what's really going on is you take the intersection, you do some geometry, you take the intersection of the view cone with the visible curb, you compute the black region, you then sample uniformly at random a point, and that becomes the value of spot. Okay. Then you want to pick a bad angle. And so in this case, the code for the bad angle is this statement right here, where range 10, 20 is basically saying you have an interval 10 to 20 degrees in this case, and you want to pick uniformly at random a value from that. Okay. And then this statement basically is saying that you're going to multiply that by either -1 or +1 to make that angle either inclined to the left or the right, okay, uniformly at random. And so that becomes your bad angle, right? So you pick a value between 10 and 20, left or right, and that's your bad angle. And then you're going to place a car left of that spot, offset by 0.5 meters. So based on where the spot is, right, the offset is basically going to be perpendicular from the curb at that point. And then you place the car, in this case, this car over here, the environment car, facing the bad angle that was sampled relative to the direction of the road at that point, right? And that's the entirety of the program. All right. And so now connected to GTA 5, each time you run it, you get a different image. Okay. What's happening, there are other attributes like the background, the time of day, the weather conditions that are not specified or constrained by the Scenic program. So every time you run the program, it will sample from the underlying distributions of those attributes, right? And that's how you get a diversity of different scenes, all of badly parked cars. Okay. So one of the attributes in Scenic is that we can do domain-specific sampling, right? So normally, if you do something like rejection sampling, you want to be able to sample from the space, but for large maps, for lots of constraints, this can be, as you might guess, fairly expensive. And so what Scenic allows you to do is prune infeasible parts of the space by essentially dilating polygons. In this case, if you're sampling from a map region, polygons that make up the map. Okay, so consider a very simple example where you have an ego vehicle that is in the environment with a taxi. And the constraints there are the distance to the taxi is less than 5 meters. And the relative angle between the car and the taxi is between 15 and 45, right? So here's actually a map of Berkeley. And what, because of the sort of the funny angle between the taxi and the car, there's a lot of sections of the road where this sort of an angle is not possible. And in Scenic, we have heuristics to compute this and rule out a whole portion of the map that you don't need to sample on, right? So in this case, the green regions are the ones that are feasible. The red outlined regions are infeasible, and Scenic will not bother to sample there, right? So it reduces the space substantially. Okay, so this is just one heuristic, and the Scenic journal paper details many others. All right, so when we first did this work, there were some early applications like generating specialized test sets to do some design space exploration. We can connect Scenic to other simulators. This case, there's a Mars rover modeled in VBots. We can debug failures of neural networks. Here's a case that we described in the PLDI paper where a car was misclassified as 3 cars, right? And you could use Scenic to do delta debugging and figure out what the problem was. We can also design training sets using synthetic data to improve performance on cases of interest. Okay, but today the main application of Scenic is going to be in conjunction with our second toolkit, Verify, which is really a multimodal toolkit that implements many techniques with many use cases. So the use cases span verification, debugging, and synthesis. We can do things like fuzz testing, which you can see already with Scenic. Each time you sample, you're sampling under constraints. So in a very similar manner as you do fuzz testing. Falsification, as I will talk about very soon. We can do failure analysis. So once you do falsification and you find counterexamples, you can try to understand the root cause of the counterexample. Similarly, once you find counterexamples, you can do data augmentation to retrain neural networks. We'll talk a little bit more about this later. You can also do synthesis of parameters, as many in the runtime verification community have worked on. On the left, the inputs to Scenic are essentially the system under verification. And in this case, the input to Verify, Verify can be connected to any simulator in theory, right? So this can be basically the implementation of the system as would run in the simulator, okay? So we've been able to do, for example, full autonomous driving stacks in Verify based on simulators that can handle that. The environment is modeled as a Scenic program typically, but we can also model it natively in Python. And the specification can be provided in a range of techniques that I will talk about soon. The key contribution of Verify is really our internal representation, which we call the semantic feature space, into which we compile our search space. And then we can search for points using sampling and optimization-based methods, simulate them, monitor for properties, and iterate that process while looking for counterexamples or other simulations of interest. Okay, and as I mentioned, there's a range of domains that we've applied this to. All right, so that brings me to the next section of our tutorial, which is talking a little bit more about falsification with Scenic and Verify. And I'll present a case study that we did with the VBot simulator. Okay, so first of all, a one-slide background on simulation-based falsification. I think this community needs no introduction to this topic because many people here have in fact done some of the seminal work on this topic. But the key idea really is in falsification, temporal logic falsification, you are going from logical formulas to objective functions, right? So in this case, you start with temporal logics that have quantitative semantics, for example, signal temporal logic or metric temporal logic. And then you turn that into an objective function that you can use for optimization. So here's a very simple example. Imagine you have this property in red in STL, which says globally at all times between 0 and tau, the distance between a vehicle and some obstacle has to exceed little delta, right? So that's your property. You can turn this in a syntax-directed fashion into this cost function, where the predicate inside, you just take the difference between the left-hand side and right-hand side. So that becomes the inside term. And then the always is turned into an infimum over the time interval, right? So you're basically looking for the smallest value of the margin between the distance and delta. And that's the value of your cost function, right? And so now you can turn the problem of verification into one of optimization. And the community has leveraged a plethora of work in numerical optimization for simulation to be able to do search for bugs, right? So if you minimize the blue function and you drive its value below 0, you've found a counterexample. Okay. Now, in Verify, we are essentially building on the work of this community. So we're not doing too much that's different. The input space is our semantic feature space. This is the space defined by the variables in the Scenic program along with their value domains or distributions. So if you're using a falsification search technique that can make use of the distributions, then Scenic makes that available to you. But if you want to use a falsification technique that ignores the distributions and just uses the domains, you can do that as well, okay? We permit multimodal specification with Verify. So we are not restricted to temporal logic. You can, of course, write your properties in something like metric or signal temporal logic, but we also allow users to specify a cost function directly. In fact, we allow users to write code that is a monitor function, a custom monitor function. So you can write a Python function that implements the monitor over the trace for the property of interest, right? So it's very general. And as Daniel will talk about later, in fact, in this conference, we've extended Verify to handle multiple objectives at the same time. So we can do multi-objective falsification. We also have a library of sampling and optimization techniques that go for the search in Verify. So for passive sampling, we have a bunch of techniques already implemented. So uniform random sampling, grid sampling, Halton sampling. Halton sampling is something we found very effective. It's a deterministic sampling technique that uniformly spreads points over the search space. We also have something called a Scenic Sampler, which is basically sample from the distribution defined by the Scenic program. But really, Verify, an open source toolkit, is designed in a way that you as a user can write your own sampler. So you can basically write a Python module that corresponds to your own passive sampler if you want, or your own active sampler. So in the area of active sampling or optimization based falsification, we have again a range of techniques like Bayesian optimization, cross entropy, simulated annealing, and so on. We also have this newer multi-arm bandit approach that was presented at RV a few days ago. But really, I think it's designed in a way that you can plug in your own falsification method into the toolkit. Okay. Oh, and then this is the new feature that I talked about, which is not just multi-objective, but we also have parallelization to speed up the search. All right, so let me tell you about the case study really quickly, and then I'll pass over to Daniel for the next section. So the case study is about falsifying a collision avoidance system. So here you've got an ego vehicle on this 3-lane road. On the left is autonomous vehicle. On the right, you've got a car that is stalled in green, and there's a bunch of cones around that car to demarcate it. Okay, now there's a camera in front of the ego vehicle, and the camera image is fed into a neural network. So normally the maroon vehicle, the ego vehicle, is doing lane keeping, but the neural network's job is to estimate the distance between the maroon car and an obstacle, which is a crash site that is demarcated with orange barriers or cones. And if it estimates the distance to be less than 15 meters, it executes a lane change. And when the lane change is complete, it goes back to lane keeping, right? So that's the task. First step is to model this in Scenic. And so in this particular approach in falsification, we're just changing the initial condition for simulation, right? So we're only using static Scenic, and Daniel will talk about the dynamic falsification later. But the idea here is you pick a site where you're going to place the stalled car. You pick spots for all the 3 cones with orientations for them. And then you place the disabled car, which is a particular object called small car, ahead of the stalled site facing a certain orientation, right? And that's the entirety of your code. We can also expose parameters for controllers that are defined in the underlying simulator if we want it, right? So Scenic really allows you to expose lower level parameters from the simulator, from the system at a high level language so that you can use this for falsification. Okay, so step 1, of course, you can just sample from the Scenic program and generate many scenes. This is a map of downtown Berkeley, for those who may recognize it, Shattuck Avenue, with the buildings taken out so you can see the roads. And so each time you sample from the program, you can get a new position on the road of the stalled car and the ego vehicle approaching it. Okay. So now what we're going to see is a simulation, a video showing the falsification in action, where, as you'll recognize, initially in falsification, you start out, you sample a point and you simulate it and you monitor the property, and you typically start with a safe or a correct simulation. And then using numerical optimization, we'll iteratively go towards behaviors that are unsafe or counterexamples. So the first simulation there was a correct maneuver. And now you're going to see more and more simulations where the ego vehicle gets closer. And in fact, in this case, it shaves a cone. And what's really happening here is Scenic every time is changing the initial position, the initial velocity, the color, the model, things like that. It's changing various parameters while getting closer and closer to the obstacle. Okay. And you can see all of these are collisions. And it's producing, a varied set of counterexamples, really. And this one is sort of an interesting counterexample at the end, where what happened was that Verify found essentially a point in the search space where this car is assigned the same shade of orange as the cone. Okay. And so using now Verify's counterexample analysis features, we can analyze this failure by looking at what we call as the counterexample table that tells us the different counterexamples we have found and do some analysis on this. We can also look at individual counterexamples and try to debug the cause. And in this case, even though the distance was 30 meters, the neural network said it was less than 15 because it saw the big car and misclassified that as a cone. Okay, but it also was not. It actually tried to do a lane change, but the lane change was done at a very low speed, and so it wasn't done properly. So using this toolkit, we were able to isolate this assumption, fix the controller, generate new data, retrain the perception module, and then make this particular error go away. Okay, so that's an example of how we do falsification using the static segment of Scenic and using some of the falsification algorithms in Verify. And with that, I will turn it over to Daniel Fremont to talk about dynamic scenarios in Scenic. Yeah, let me stop sharing and Daniel can share from his laptop. And Daniel,
can you hear me? Can you hear me now?
Yeah.
Okay, thanks. Morning/evening, everybody. Let me switch over to my slides here. Okay, can you see this?
Yes, we can see.
Yes, we can see
Okay,
your slides.
great.
Yes.
Okay, so as Sanjit said, I'm going to start out by talking about some extensions we added to Scenic more recently, allowing you to encode dynamic scenarios, not just initial conditions like we saw in the last example. And then from there, we'll talk about how you can go from falsification to actually doing delta debugging, as Sanjit mentioned, and actually using that to improve the performance of your system through intelligent retraining. So to start out here, let me talk about the features in Scenic for going beyond initial conditions to describe dynamic agents and how they behave over time. So for instance, we had the badly parked car example, which Sanjit showed earlier, where you can specify not only the distribution on the car's position, but also some distribution over a policy for that car, saying how it should behave. And we call that policy a behavior. And Scenic has syntax for specifying behaviors in a variety of different ways. So this is a snippet of code similar to what we saw before, where we're specifying the initial position of the car, its orientation, but also the behavior we're saying is given by this behavior pull into road. So how do we specify behaviors? So first of all, just to get a sense of how these behaviors work, you can think of a behavior as a function which is running in parallel with the simulation. And at each time step, that behavior executing inside Scenic issues an action. So we might have a variety of behaviors, one for each dynamic agent. At each time step, they choose an action to take, which we think of as like an atomic decision that an agent could take at one time step. For instance, for autonomous vehicles, it could be something like set the throttle to this number, or steer at this angle, turn on your turn signal, something like that. So those get gathered together by Scenic. They're sent over to our simulator then, which then advances time by one time step. So it can simulate the physics, render the image, simulate whatever kind of sensors your system needs and so forth. And the idea is that Scenic itself, in order to be agnostic to domain and to particular simulators, doesn't have any of these actions built in. They are defined in a Scenic library for whatever application domain you're using. So for instance, our generic driving model, which works in a number of simulators like Carla and LGSVL, we'll see later, defines generic actions like throttle, braking, and so forth, which can then be implemented in specific simulator interfaces. So you can actually write a Scenic program that talks about that defines a driving scenario once and then use that in multiple different driving simulators. And yeah, so as I just said, this allows you to basically abstract away details of how the interface works. So you can have multiple simulators use the same generic Scenic program. And these behaviors, in order to decide which actions to take, can access the state of the simulation. So they can look at, what's my current position? How close am I to other cars, for instance, all that sort of thing. And we do that by reading back from the simulator at every time step the current state of the simulation. So for instance, we might implement a behavior for following a lane, something like this. It's an infinite loop where at each time step, we pick some throttle and steering by some expressions based on the current position, say, relative to the position of the lane. And then we choose our throttle and steering appropriately. And so in this function, you can access things like the position of the lane, your own position, and so forth. And here we can already see some sort of simple temporal aspects going on. This infinite loop is one where it's iterating once every time step. This take statement in Scenic says essentially, issue these actions, now wait for the simulation to proceed by one time step before resuming execution of this behavior. But you can do more interesting things with some of Scenic's temporal constructs. So in particular, two that are quite useful are interrupts, which allow you to add special cases to behaviors without modifying their code. So for example, in our Scenic library, driving library, we have a generic behavior for following a lane at a given speed. And obviously that would be useful in a variety of different scenarios. But now suppose you want to do something specific, like follow the lane at a certain speed, but when you get sufficiently close to another car, do something else, some collision avoidance maneuver. We can do that in Scenic with an interrupt. So what's going on here is we're saying you do this follow lane behavior, but you monitor this condition, that the distance to some other car might drop below some safety distance. If that condition is met, you suspend the follow lane behavior, switch to this collision avoidance behavior. And when the collision avoidance behavior completes, if this condition is not true anymore, we will resume the follow lane behavior. So this essentially allows us to add some new behavior onto this follow lane behavior without having to open it up and change its code. So this allows us to make modular libraries of behaviors. We also have the ability to impose temporal requirements. So we saw some static requirements Sanjit mentioned before. For instance, you could say, require that the angle between these two cars is in a certain range. We can do the same thing over time. So for instance, we could require that this taxi object has to always be in a particular lane. And Scenic will enforce this requirement. So if some simulation would violate this requirement, it will throw it out and generate a new simulation. We can do something similar here, for instance, to say that at some point, the ego must be able to see the pedestrian. Otherwise, we don't care about this simulation. And in general, there's actually a syntax for defining arbitrary monitors, not just this simple kind of always or eventually properties. So to show a little bit more detailed example here, this is a Scenic program based on one of the scenarios in the OAS Voyage scenario database. The idea is you're going to have a lead car, which is periodically stopping and starting, and the ego car, which is following it, has to brake to avoid a collision. And we're going to write this in a way that it works in multiple different driving simulators. So we'll start out with a follow lead car behavior. This is actually the same one we just saw on the previous slide. That's what the ego car's behavior is going to be. And now for the lead car, which is stopping and starting, we can do something a little bit more complicated. So here we're picking a random time, the delay between when we're going to be stopping and starting to be between 3 and 6 seconds. And then we're going to do a follow lane behavior, but when it has been that amount of time since the last time we stopped, we'll then brake for 5 seconds, update our state here, which is storing the last time that we stopped, and then resume. So what you'll get is a car which is periodically pausing for 5 seconds. Okay, and then we can set up the positions of the cars. So we'll say the ego car can be uses default position distribution, which is uniformly at random over the entire map. Using this follow lead car behavior, we'll start out the lead car 10 meters ahead of the ego. And just to make sure that this simulation has enough space ahead in the road, we don't want to be like in a cul-de-sac where there's a dead end or something. We're going to require that there's at least 100 meters of free space ahead of the ego. And finally, we'll add a termination condition here, which is saying that if the ego goes out of a lane, then we can terminate. This means, for example, if we enter an intersection, we'll terminate the scenario. Okay, so if we now sample from this scenario, the Scenic tool can execute this scenario in a number of different simulators. So for instance, here it is running in Carla. So you can see the cars start going, the lead car stops, and the ego car successfully brakes. Now, once the lead car starts again, they keep going, etc. So this is just a simple example of a scenario. And we can do the same thing in LGSVL. So here is the exact same code now running in the LGSVL simulator in a different map, different models for the cars and so forth, but the same overall behavior. In this one, there's actually a collision because I think the mass of the car is greater. In this one, it can't stop in time with the threshold that we set. Another thing I want to mention is that Scenic has syntax which allows you to compose simple scenarios into more complex ones through various forms of composition. So for instance, we could import from some other file 2 scenarios for maybe the stopping and starting car and the badly parked car, and we could compose them in parallel like this. So that would say run these at the same time, or sequentially. So do the stop and start scenario followed by the badly parked car scenario. And you can do more interesting things as well, like maybe start out with the stop and start scenario, but under certain conditions, switch the start the badly parked car scenario. So this makes it easier to build fairly complex scenarios by reusing elements that you've previously defined. Okay, So getting back to falsification, we can do falsification much in the way that Sanjit showed before, just now controlling the dynamics as well as the initial condition. So this example is from the case study we did in Carla, which you can find in this archive papers. This is the upcoming journal version of the Scenic paper, where the scenario is there's an AV which is trying to turn right at a four-way intersection. The traffic light is originally red, but it turns green as the AV approaches. But then somebody else coming from another direction runs the red light. They go through as the light is changing. And so the AV has to be careful not to collide with it. So the semantic features that we varied here were which intersection the scenario takes place at, the timing of the traffic light, and the speed of the car. And we can do falsification in verify, sampling from this scenario and monitoring specs like the cars should not collide, for instance, and then analyze the results. So for instance, this is showing the row, the quantitative satisfaction value that Sanjit mentioned before for a collision specification, a non-collision specification, as a function of the position of the cars. So this is basically showing that certain intersections are more dangerous than others. So for instance, these green ones, the car was always safe at, whereas this dark red one here, all the simulations we did at that intersection led to counterexamples where a collision occurred. And some were in between. They may not have had collisions, but they were in dangerous situations where you came close to a collision. We can also plot these results with respect to other parameters, for instance. So I mentioned like the traffic light timing, which here was parameterized by a threshold distance from the intersection, and the crossing car speed. And so we can see interesting things here, like most of the unsafe scenarios, the deeper red dots here, occurred near a particular value of the threshold for when the traffic lights would change. Okay, so I want to show a quick demo. I think we have time here just to show you how you can play around with some of this yourself. I'm not going to use one of the more complicated simulators here because you have to install it and so forth. We have a simple Newtonian physics simulator built into Scenic, mainly for testing purposes, if you just want to give it a try. And I've put the instructions here. We'll post the slides later on so that you have all this. It's slightly involved right now because I'm going to use some features which are in this branch that we haven't merged in yet. But we'll should get this all merged in soon, and then it'll be easier to do. So if I'll just switch over momentarily, let me share a different part of my screen.
Daniel?
Yes.
When you're sharing, make sure to hit the button to optimize for video if you're showing a video.
Oh, yes. Actually, it's grayed out. I wonder if there's some section of configuration thing for the meeting I can't change.
Okay.
Anyway, yeah, so sorry about that. Let me at least share the, we'll see what we can do. Okay. So can you see this?
Oh. Yeah, I see an empty screen and a terminal.
And a terminal, right? Okay, great. So what we're going to do here is run one of these scenarios. Let me just show it to you very briefly. So this is a scenario that one of our colleagues developed that I just described as four-way intersection one. I won't go through the details. Some main things to point out, we're using a particular map in Carla. This one is designed to be run in the Carla simulator, although you could easily port it to a different simulator. We're going to be using Halton sampling for falsification, which Sanjit mentioned earlier. And so we're doing things like specifying ranges for various parameters. One thing that I want to point out is that in Scenic, you can, instead of putting a fixed distribution on a parameter, you can allow verify to do search over that parameter. So what this is saying, for example, is use verify's search techniques to find a value in the range 7 to 10 that hopefully leads to a counterexample. So here we're using Halton sampling, but you could use Bayesian optimization or some other technique to intelligently search through these ranges. So you don't just have to have a fixed distribution. We can kind of combine random distributions in Scenic with intelligent search techniques. And then we have a definition of a behavior, which is quite similar to what we saw before. I won't go through that. We're laying out the geometry by picking, from the entire road network at a random four-way intersection and so forth. And then finally, we're positioning the cars relative to that. So it's quite similar to what we just saw. And now if we run this, what you will see, if this comes up in a moment. So it's interpreting the script. Okay, and here we go. Now it's starting the simulation. So this is in our simple schematic simulator that just renders a kind of a schematic view of the road network. And you can see the car which is going straight here, the car which is trying to turn left, and we're already getting some counterexamples here where there are collisions. So I'll just let this finish. I think I've set it to do 5 different runs. So that last one looked like it was safe there. There's another collision. Okay, so this is finished. And now if we look at the output from this, we get a CSV file, which basically says all the values for the semantic features. So here we have, for example, object 0's color. It has 3 coordinates, its heading, its position, and so forth. And also some of these other parameters we had, like the speed of the adversarial car, how much we braked, and so forth. And then at the end, we have this row value, which is the quantitative satisfaction value of the specification. So in this case, this first run, for instance, very slightly violated the specification. And so Verify then has techniques which could read this data in and cluster them or do some other kind of analysis. Okay. So I'll switch back. Okay, so just the last thing that I want to mention briefly, is, as Sanjit also mentioned before, we have a paper appearing in RV this week, which our colleague Kesav Viswanathan presented on Monday, with some new features in the Verify toolkit to help with falsification. One is now Verify has the ability to run multiple simulations in parallel. And since the simulation time for most of the use cases is the bottleneck here, that can greatly increase the number of samples that falsification can generate. We also have the ability to do multi-objective falsification. You can specify a variety of different specifications and a hierarchy, giving priorities between them. So you can say, for example, here that maybe specifications 1 and 2 are sort of equally incomparable. They're not, one is not more important than the other, but specifications 3 and 4 are less important than they are. And we have a new sampler based on multi-arm bandit techniques, which can use this information to try to falsify the most important specifications and as many specifications at once as it can. And another nice feature that this multi-arm bandit sampler provides is it gives a trade-off between exploration and exploitation. Most of the samplers we had already in Verify are sort of on one end or the other. So for instance, we had samplers like cross-entropy optimization that are on the exploitation side. They really just try to zero in and find a counterexample. They're not concerned beyond that point to get like a good spread over the space. Conversely, we have things like Halton, which just give you a good spread over the whole space, but do not try to zero in on counterexamples. And multi-arm bandit is somewhere in the middle. It clearly can concentrate its effort on the areas where there are more counterexamples. You can see that it's done a lot of sampling in this region where over on the cross-entropy side, you can see there are many counterexamples too. But it's still giving you some coverage in areas where there aren't that many counterexamples, unlike cross-entropy. So that's it for dynamic scenarios in Scenic. Let me now say just a little bit about how you can go beyond falsification to some other use cases. And then I think we'll pause for questions. Okay, so this case study, which I mean, actually I see we're a little behind time here, so I'll go through this fairly quickly. This case study was designed to demonstrate how, in addition to discovering failures, Verify can help you debug and fix them. So we did a case study on this TaxiNet system designed by Boeing that uses a neural network to navigate an airplane on the runway. And we went through a whole iteration of a design process for this, modeling the operation scenario for the system, falsifying the system, debugging to find distinct failures and diagnose the reasons for those failures, and finally retraining the system to eliminate some of those failures and improve performance overall. So this TaxiNet system, as I mentioned, uses a neural network to take an image like this one and then estimate the cross-track error, which is the distance to left or right of the center line of the runway. Then that goes into a controller to generate the steering and throttle controls for the aircraft. And the specification we had for the entire system was that the plane must track its center line to within 1.5 meters. And we used actually a somewhat looser specification to allow starting not quite on the center line. So we required, this is a specification in signal temporal logic, which says that within 10 seconds, you have to get within 1.5 meters of the center line and then stay there for the remainder of time. So this was the specification we used. Then we could model this environment in a scenic program where we have a variety of semantic features like the time of day, type of clouds, position of the plane, and so forth. So this is actually the complete scenic program we used. I won't go through it in detail, but you can see that we're setting up ranges for the time of day, some distribution on the clouds, which is actually a joint distribution with rain, because you can't have rain unless you have certain kinds of clouds, and some ranges for the position of the plane as well. Then we ran 4,000 or so simulations from this, and we found actually quite a few counterexamples. Almost half of the runs violated this property, and in 9% of them, the plane actually left the runway entirely. So then you want to know, why did these failures happen? So in fact, we found a number of different types of failures, for instance, sensitivity to time. So this is plotting all of the simulations as a function of time of day from 6 a.m. to 6 p.m. And the y-axis here is the robustness value of that specification we saw before. So positive means it was satisfied, negative means it was violated. And you can see there's quite a strong dependence on time. I'm showing the median here just for clarity. You can see that it does quite well in general, for instance, around noon, whereas later in the afternoon, it does worse, and also early in the morning. So to try to understand what was going on here, we looked at some of the runs that we generated, and we noticed that, for instance, if you compare 12 p.m. to 4 p.m., leaving all other semantic features the same, there's a significant difference, namely the shadow of the plane intrudes into the image. So maybe that is what is confusing the neural network. And indeed, it's easy to do follow-up experiments that confirm that this was actually the reason. We can just change the scenic program to basically say, okay, now leave everything fixed except the time, and then you either turn rendering of shadows on or off. Okay, so now that we've identified failures like that, we can use Verify to help fix those by generating a specialized training set. So here, actually, we generated a completely new training set that was the same size as the original, but now using that scenic program to ensure we got a good variety over times of day and so forth. Whereas the original training set was given to us by Boeing, we didn't know which images were in it. And indeed, we got much better performance by using this training set. So you can see here are two identical runs. The top one is showing the original system, which actually leaves the center line and eventually completely leaves the runway, whereas the retrained system on the bottom consistently tracks the center line accurately. And this is just one example, but overall, we saw much better performance. The rate of satisfying the specification improved, and the rate of completely leaving the runway substantially improved. And you can see here that we've actually eliminated the dependence on time of day. So the new retrained system is shown in blue, and you can see it's consistent over the entire time period. In fact, you can actually use the cross-entropy method to learn a good training distribution rather than writing it by hand in the Scenic program. But since we don't have a ton of time, I won't get into that now. We can come back to it later if folks have questions. So just to conclude this section, we show that Verify can be applied to realistic industrial autonomous systems, and you can use it to both find bugs and diagnose them, but also eliminate some of them through more intelligent training set design. So here we found a particular bug, identified a hypothesis for why that bug happened, verified that hypothesis, generated a new training set that improved the performance of the system. But of course, not all counterexamples can be eliminated through retraining. We saw even with our retraining, we still had a substantial fraction of the runs where you violated the spec. So then that leads to a natural question of how can we use runtime monitoring to handle those situations? And that's what Sebastian's going to be talking about next.
Yes.
Before we go on to that, the next section, are there any questions?
Actually, I would have a number of questions. I have many questions, but maybe I would like first to see if any of the participants.
Thank you for the wonderful tutorial. So I have maybe two questions. The first question is, you showed us a couple of like different scenarios in simulators like Kala. I'm wondering, is it possible to using the Scenic language to simulate behaviors like pedestrians or any other kind of humans, which may be different from the other cars or obstacles?
Yeah. Yes.
Daniel, I can do it. Yeah. So yes, absolutely. In fact, we've done that. So Sanjit will mention it towards the end of the talk. A scenario we did with exactly that. We had a pedestrian walking into the road. And so there, you just in the same way you can specify the behavior for a vehicle, you can write a model for the way the pedestrian behaves. And if the simulator supports pedestrians as objects, then you can treat them just like any other type. So Scenic actually doesn't really have anything built in about cars specifically. We've tried to make it as generic as possible. So we have written scenarios involving pedestrians, vehicles, aircraft, all sorts of different dynamic agents.
So the question is, how do you actually model the pedestrian's behavior? It's slightly different, like vehicle dynamics. Usually you can find some papers or something talk about that.
That's a really good question. And I think it's still an open research question. So Scenic is a language, right? It provides you with many ways to do that. One way is you can take learned models based on techniques like IRL that many of us have seen and used. And you can expose parameters of that learned model in Scenic. So you can have variants of a learned model that are controlled from Scenic. But really, I mean, it's you can also have a very programmatic model that I'll show you at the end of the presentation, where everything is pre-programmed and there is no lower level model controlling the pedestrian. So there's a spectrum of ways that you can do it.
Great,
so
thank you.
In other words, it's very complementary to that question that you asked.
Thank you. My second question is about the. I think these two, Scenic and Verify AI, is great for both research and education purpose. And I'm wondering, what is the learning curve to say if we want graduate students taking classes to do maybe a project or something using these two? What is the learning curve? Does your team already developed some more in-depth tutorials or some project-based for that?
Yeah, so we have fairly substantial documentation on both Scenic and Verify, although it can always be improved. And we've had experience with both industry people who are not really, have no formal methods experience, being able to write Scenic programs with fairly little runway. And also students in my graduate class and even undergrads use it. Having said that, I don't think we've done a systematic study of the usability and of these tools. And I think the tutorial materials can obviously be improved. So feedback is welcome from any of you who want to try it out. Okay, maybe in the interest of time, we should proceed with the next part, and then I'm eager to hear all your questions, Dian.
I would also propose that, so to give the chance also to Sebastian to present his part, and let's continue with the questions at the end of the tutorial.
Yes, thanks. I hope you can hear me and you can see the slides full screen. Yes, great. Okay, so let me quickly recap, right? So in the next 20 minutes, what we want to present is how Scenic and Verify are it can be used to generate and analyze runtime monitors. And my name is Sebastian. I will guide you through this part. And so runtime monitors are important in various contexts. You can name more than I can. But within this tutorial, we're going to focus on a runtime monitor as a decision module in a simplex architecture. And so in a nutshell, such a simplex architecture has two controllers running in parallel, an advanced one and a safe one. The advanced one can fulfill all the functionality that the system should have, whereas the safe one can fulfill safety. And so you want to use the advanced controller as much as possible, but every now and then you'll need to decide to go back to the safe controller, because as Daniel showed before, like absolute safety with neural networks is still a big challenge. So sometimes we'll need to go back to a safe controller, and we want to generate monitors that can make this decision at runtime. And so this scheme represents verify, as you've seen before. And we are discussing an extension to that will allow the automatic extraction of decision modules of the system. And in particular, we will do that based on the data that we're collecting with the sampler that we've also been talking about before. So you can all probably already imagine a little bit how this could look like. And this slide gives away the main approach. We obtain by adequate sampling positive and negative examples, where a negative example is a trace of observations where at the end one wants to raise an alert. And the goal of the monitor generation is then to generalize these negative examples to also include unseen traces. And that is, you want to generate this decision module that sees a trace and then decides to raise an alert or not. And this task is not easy. The traces are encodings where at every step we have all the properties of the system and its environment, so it's highly dimensional. There's probably continuous data in it. Lots of the information may be available during simulation, but not at runtime. So the precise position of another car, the intent of other agents is all not known. And some sensors, like camera sensors, are sometimes not reliable if it's rain or fog. And so we need to project this down to reliable data. And then, of course, we want a monitor that does not raise a flag after we crash, but rather before, and all the other challenges that you all know from runtime monitoring that I'm not gonna repeat here. And so, as I said, we're looking at a data-driven monitor generation because we simply do not have a model of the full autonomous stack and the full environment that we're running in. And this works basically in 3 steps: data preparation, monitor generation, and monitor implementation. I'll focus on the first 2. In particular, data preparation itself can again be thought of as 3 steps, where we're gonna map, segment, and then disambiguate our traces. Mapping, the first phase, takes the simulation data and tries to generate data from that is observable at runtime. And so that can be used as a basis for our decision making. This is then again 2 phases. The first one, projections. What it does is basically on a per time step basis says, these are the available information that we had at simulation time, and we're mapping that to information that's available at runtime. And this might be depending on so this might be a complex function. It's not simply extracting things or excluding things, but it can be more complex function. So that's straightforward, I think. And then we'll need filters. Filters are basically mapping traces to other traces. Well, this is a very general function, and what we're actually looking at are these kinds of filters which have an internal state. So we have an input and a state, and we map it to an output and to a successor state. And the important thing is that when we're using these filters during the mapping phase, then we'll also need to implement these filters on the runtime system to actually work. And why do we need these two things. Well, projections can be used, for example, when it's rainy, we do not want to include a camera in the observable data. We might have a very cheap temperature sensor, which we deem not reliable, so we want to exclude that, and so forth. Filters are useful if you want to aggregate the number of deviations in the past, basically to have an online estimation on whether you're trusting your sensor right now, or because you maybe want to smoothen your GPS position to make it more reliable. And so with that, we're getting to a set of data which we want to use for our decision making. And now what we want to do is we want to construct monitors which are mostly relying on what has recently been happening. It also, by making these windows, we obtain more data cheaply by just saying one trace is a lot of data. And so we are taking this sliding window approach. And then for every window, we need to decide whether we should raise an alarm or not. And we do that as follows. We define a temporal property and if from the future onwards, after the input segment, if this property is satisfied, then we label it as a positive example, and otherwise we label it as a negative example. So then we have labeled data where all the data is observable. What might happen if we do this is that we might introduce duplicates, and most of the downstream algorithms somehow require us to handle duplicates right from the start. And so there are a couple of choices that you can make. Either you say, well, if one of them is a negative example, like we are labeling it negatively, or we can take a more quantitative approach here. But in the interest of time, I don't want to go into details there. So, but the result of this data preparation step is then that we've obtained finitely many positive and negative examples. And with that, we're going to the monitor generation. And I want to discuss three aspects today: the implementability of it, the quantitative correctness, and the trustworthiness of these monitors. So first, implementability. So very important for implementability is the realizability, right? Can we actually obtain all the data that the monitor is talking about during runtime? And we're already taking care of that step during the data generation phase. The second important thing is, of course, the performance of such a monitor generation. And I think what we're taking care of in this part is that we are making sure that the logic cannot be too complicated. So we're trying to get artifacts which where the logic is not too complicated. I can talk about this a little bit more afterwards. What I do want to stress here is that we think that AI systems are often computationally more heavy than maybe your sensor system is, or your traditional network system. So we do have a little bit of power available on these systems typically. And then we also need to talk about correctness. And absolute correctness of such a monitor is a very hard goal because we're working with finite amounts of data. And without any additional goal, this is going to be very hard. Of course, the typical verification view is, well, if you should be absolutely sure. And so that would mean that we're going to raise an alarm on everything which we haven't seen and on everything where we've seen that it's actually negative. But then we are so conservative that we're not useful anymore, right? We would be constantly in the safe controller, and this is just not useful. So we would argue that we need a quantitative measure of correctness. And of course, in a safety critical situation, we should distinguish false positives and false negatives, because one of them is just bad luck that we're moving a little bit too often to the safe controller, whereas the other one, we would stay in the advanced controller and potentially get into a safety critical situation. And so what that also means that we can use this as a guideline to discuss what kind of algorithms we actually want to use. Basically, you can look into the literature and find either exact or peg learning algorithms. And the exact learning algorithms, they come with a very nice guarantee that they're 100% correct on the training set. But we've seen that they're often overfitting, and you won't have any guarantees outside of the training set. So of course, if you have a huge training set, which might have been agreed on by a couple of governing bodies, then this is very helpful. But outside of that, the guarantees are very weak. Back learning yields a stronger guarantee, but maybe arbitrarily off anyways. But like empirically, it's correct in most cases. And you can use, you can learn now different artifacts, either automata, decision trees, or neural network classifiers. And we've done a pack approach for all three of them, and these are available in Verify. Of course, there's possible other extensions, other targets, and it's quite modular, so you can just plug in your own algorithm. And I think there's a lot of room for collaboration and improvements here. But coming back to the fact that we're running now with a quantitative correctness measure, the elephant in the room really is like, what are we gaining? We have a system, we are empirically already quite happy with it, and now we're adding something on top of it, where we cannot provide an absolute safety guarantee. And so what the key here really is that our monitors empirically make the system safer. And we can actually show that by putting the monitor in the loop and then run Verify again. So what do I mean by that? After we generate a monitor, we're basically putting the monitor on top of the system. And then we again have a system which we can run through our simulation, falsification algorithms and everything. And so this is the simplex architecture. We really make that part of our system and then rerun everything, and can use it to actually find new weaknesses of the monitor and improve our decision model generation. So with that, we at least hope that we're addressing the trustworthiness issue. So the last part I already said I won't be talking about. It's the monitor implementation itself, and really what we're currently doing and what we think we can even do better by collaborating with you guys is to basically just leverage the work that has already been done in this community. So that's that. Now we're going to the videos again. So we did not just develop these parts, but we also implemented them and applied them to the TextNet example and some other examples. But I want to talk about the TextNet that Daniel already presented. And so now we're running a system with a decision module that we've been learning using Verify. And so this is the first video. So here we learned a monitor which only takes static features. So if I start the video, then we're in a situation here with this initial line, and in particular the shadows, which are probably cut off a little bit, are problematic. And so we've learned that this is an untrusted environment, and we raised this alert. And now if I continue the video, it's not a big surprise that indeed this will well not work that well. I should say that we are actually running the retrained TextNet that Daniel showed, like the way where we already improved TextNet. Okay, so in other situations here, we run the same monitor with the same things. You can, oh, this is not the next slide. This is the next slide. And here's the start. So here, there's not this much shadow because of the overcast weather, and we're trusting this environment. We'll finish the video, but you can see that indeed this works better. Of course, there's no absolute guarantee that when we say it's a trusted environment, that it's always a situation where it's good. but we're improving upon the, like we have a high positive and or low false and positive negatives. Okay, so this is for static features. We can also do the same thing with dynamic features. So first, I want to show you a video in which we let the monitor run, but we basically disabled it as a decision module. So we are not switching over from the advanced controller to a safe controller. And initially, everything is fine. We're still in this overcast situation. And now there's these marks on the ground on the runway. And what will happen is that we're gonna slightly deviate. We're deviating more and more, and now the monitor also says, well, this doesn't look good. I don't really trust this anymore. But what happens is that we stay away from this situation quite a bit. So there's the system remains unsafe. Indeed, if we now add the simplex and switch back to the safe controller as soon as we raise an alert, then in exactly the same situation, we will see that this makes the system more safe. Yeah, I'll just let the system run. But here, these are very nice experiments to run with Verify and Scenic, because you can very flexibly say we want to keep everything the same and rerun it with this particular monitor in place. So here the alert comes in and we immediately run a safe controller, which is mimicking a human intervention. And then we're oscillating a little bit, but at least we're making sure that we stay close to the cross-track. And with that, oh, that was the wrong button. Sorry about that. I want to summarize. Oh, sorry about this. Yeah, so in summary, what we did is we learned decision modules from data sampled and processed with Verify. And then we can evaluate the system with and without this monitor, again, using Verify and Scenic. Nevertheless, there are plenty of open and ongoing topics here, among which there is creating efficient implementations from the logic that we described by our monitors. Feature selection, what features are reliable, what features are not reliable. We're currently purely data-driven black box. We are not using any information from the Scenic program or other models. There's certainly room for that. And we think that we can also integrate learning of these models more into the system itself. So we're absolutely happy to cooperate. We think there's a lot of interesting things going on in the runtime verification community that could help us here. And with that, I want to hand it over to Sanjit again.
Thank you, Sebastian. Can you see the slides in full screen mode?
Yes.
Yeah. Okay, great.
Yes.
So I want to start out by summarizing the features of the two tools we presented today. So first of all, on Scenic, there are many language features that we went through. So you can specify these classes, have different types of objects. You have basic support for geometry and distributions. You have this notion of a local coordinate system that we touched upon, where every object has a local coordinate system and you can specify attributes relative to that. We didn't talk a lot about this, but we have this notion of specifiers that you saw for specifying attributes of different objects. We can add declarative constraints. We can have parameters that can be controlled externally, as was done for the Boeing case study. And then for the dynamic behaviors, you can specify agent behaviors, actions, notion of interrupts and termination. put monitors and temporal constraints and also various constructs for composing scenarios. On the side of verify, for use cases, we can use the combination of Scenic and verify for various use cases like synthetic data generation, test generation, requirement specification in a multimodal fashion, falsification, debugging and error explanation, data augmentation to then do retraining, goal-directed parameter synthesis, and now runtime monitor generation that Sebastian just talked about, right? And I think we really designed this toolkit to be extensible in this way. And as we've said many times, we'd love to collaborate with the community on this. There is a reasonable amount of documentation on both Scenic and Verify. We have a tutorial style description. These are linked to from the GitHub pages for both distributions. So I want to end in the next few minutes with just a quick summary of some ongoing and future directions. So one piece of work, the animation is a little bit messed up here. I'll come back to this one. So this is work that we published at CAB earlier this year. I'll get back to it. We've been doing a lot of work on verified human-robot collaboration. And some of this relates to Lu Feng's question. And a lot of that can be experimented with using Scenic. So you can take these learned models of human behaviors and we can experiment with that in using our tools in a simulator. We've done work on programming runtime assurance systems like the Simplex architecture, the SOTA framework, where you can, when we just give programming language support for creating Simplex-based systems. We've done work on using Scenic to debug, to explain cases where deep learning succeeds or fails. And we've done work on bridging between simulation and the real world, both in terms of metrics to compare simulated versus real trajectories, as well as designing real world test cases using falsification. I'll talk about this in the next 2 slides. And then coming back to the first picture, we've done work on runtime monitoring in uncertain environments that are modeled as MDPs. And this is work that was presented at CAB earlier this year. So there's many ongoing directions related to the work we've presented, and we'll be happy to talk offline about any of these. Let me just quickly mention this topic of bridging simulation to the real world, because I think this is of interest to many in our community. A lot of work is done in simulation. The question is, well, if you find a counterexample in simulation, can that actually happen in reality? And so we've done multiple studies on this. I want to talk about our ITSC paper. So here we did a collaboration with the American Automobile Association, which runs one of the largest AV test facilities in the country, and LG, which supplies the LG SVL simulator that was mentioned earlier. And in this case study in AAA's testing grounds, which you see a little map on the right, we ran a scenario where the autonomous vehicle, which you see here on the left, it starts at the bottom right corner. It follows this blue trajectory and it has to end at the top right. But at this point, it has to, when it turns right, there's a yield sign and there's a pedestrian crosswalk. And we modeled a scenario where a pedestrian, in this case, implemented by an actuated pedestrian dummy, starts off at the yellow dot and then wants to go to the red dot, but hesitates in between at the orange dot. Okay. So this scenario was modeled in Scenic, and here's just a snippet of the relevant program where here's the model of the ego vehicle with a particular behavior, which is it starts at a certain location and has to end at a certain location. The pedestrian, as somebody asked earlier, right, in this case is modeled using a very simplistic programmatic behavior, which is modeled as this hesitate function. So it's really the composition of 3 behaviors, right? The pedestrian starts at the yellow dot, moves at a certain velocity, which is limited by the pedestrian dummy, to some point, which is chosen at random. So this is the walk distance chosen uniformly between 4 and 7 meters. The dummy starts moving anytime between 5 and 15 seconds after the car starts moving. So that's another random variable. And it hesitates for between 1 and 3 seconds while in the middle of the road. Okay, so it's modeling the scenario where a pedestrian starts crossing and then hesitates in the middle of the road for some random period of time, and then decides to continue on. And you can also do things where the pedestrian backs up and so on. Okay, so then we ran falsification and simulation in the LGSVL simulator, and we found lots of counterexamples. We did an analysis on the counterexamples and then used that to select test cases that we thought would be good test cases to run on the road. And these are test cases where we use the robustness value of the temporal logic property, the MTL property, to be able to find out where the behavior was at the boundary of safe and unsafe, for example, or whether it was robustly safe or robustly unsafe. So what we found in our study is that when a behavior was unsafe in simulation, it was usually unsafe on the road, right? So more than half of the trajectories that were unsafe in simulation were unsafe on the road, where unsafe means that the car comes within a certain small distance of the pedestrian dummy. And then we found that overwhelmingly, those that were safe in simulation were safe on the road. Okay, and here I'm going to show you one particular case study. This is one of the cases which was unsafe in simulation. We ran this on the road. You're going to see the car come up on the turn, and the pedestrian dummy starts moving across. You see the car stops. It actually detects, the neural network detects the pedestrian dummy, but then it goes ahead and hits the dummy anyway, right? So this is one of the failures that we found in simulation, and then we were able to replicate this on the road as well. And then we also did some analysis later to try to diagnose what the root cause is. So just to give you an example of how Scenic and Verify can be used not only in simulation, but also effectively to design real-world tests. Okay, so I want to conclude by going back to the challenges for verified AI that I talked about at the beginning of the talk, and just summarize the principles that we presented back in 2016, and then just summarize it for the audience here. What are some of the things that we've learned along the way? So for environment modeling, we've been following a three-pronged strategy to do this. So data-driven modeling is basically learning models from data, particularly relevant for modeling human behavior. So probabilistic modeling is what Scenic does, which we think is really crucial in this domain. And introspective environment modeling is a technique that I talked about back at RV 2019, which is basically how to come up with models when you don't know which are the agents in the environment. You can't really write a Scenic program with some degree of certainty, and you want to be able to extract assumptions from the system itself. For specification, our approach is really to model the whole system and then derive component level specifications for example, neural network components from the system level behaviors. For dealing with learning systems complexity, we're relying on the very same techniques that the formal methods community has worked on, so do abstractions. But also we think the semantic representation that is provided by a language like Scenic is absolutely crucial because it raises the level of abstraction and makes verification more scalable, right? And so I think in addition to doing semantics directed search, we also think compositional analysis is absolutely important here. And finally, for doing design for correctness, there are two major techniques we are proposing. One is to do what is called oracle-guided inductive synthesis, oracle-guided learning, where you pair standard machine learning techniques and training methods with oracles like verifiers or falsifiers or other kinds of oracles that can help improve the overall reliability. This was the kind of thing that was done in counterexample guided retraining that we talked about earlier. And finally, runtime assurance is absolutely critical in this kinds of systems because you can't really model the environment with perfection a priori. And so you do need to model, be able to handle unexpected scenarios at runtime. Okay, with that, I'd like to conclude here. So thank you all for your attention. I think this remains a very exciting area. And now we would love to take your questions. Okay, thank you.
Thank you very much for this very exciting and really beautiful tutorial. So we are already a bit late, but we will still have some questions. So I would like to invite the audience to ask questions about the tutorial.
I have a question, Diane, if I may.
Please.
So thank you very much for the interesting presentation. I was wondering if, so we saw how you distribute the scenarios and you see the coverage along different dimensions. I was wondering if you have some more formal formal notion of coverage criteria for test generation, either based on the environmental model or on the AI model, or different kinds of possibilities are there. So do you have any such coverage criteria in mind?
Daniel, do you want to take that? But let me just quickly preface that by saying that our tools that we talked about today are agnostic to the particular coverage metrics that you may have. So you can actually program any coverage metric of interest. Mm-hmm. But having said that, there's a few that we've experimented with. So one sort of coverage comes in with the Halton sampling, which has a built-in notion of coverage that allows it to kind of uniformly spread points over the sample space. But there are others as well. Daniel, do you want to comment on this?
I think all I would add to that is, yeah, we don't particularly have, we don't have many metrics built into Verify, but as Sanjit said, it's easy to, you could add more. There is this concept of low discrepancy sampling that Sanjit was talking about for Halton sampling. I think there are other notions of coverage that people have looked at for these types of systems. For example, there are notions of coverage for neural networks, for instance, right, where you look at how many different types of activation patterns in the network have been covered. We don't have code for that integrated in Verify because we treat the system as a black box. So we don't look internally, but it would be very easy to add, for example, a new sampler to Verify, which computed that notion of coverage for all the runs you've done so far, and then use that to decide which test cases to try out next. And that is a direction, as I think Sanjit mentioned, that we're definitely interested in heading in, trying to do more white box analysis of the system. Whereas to start with, in order to be as scalable as possible, we treated the system as a complete black box.
Right. And I should add that the Halton sampling method, the low discrepancy sampling, that was a technique that we borrowed from literature in the robotics community, where it's been found useful for things like sampling for randomized planning. So sampling in spatial environments.
Are there other questions?
Hi, I have a quick question. You showed really nice on-ground scenario generations. Is it also possible to generate in-air scenarios for aircraft, for instance?
Yeah, yes, in principle, yes. You can generate in-air scenarios as well. We did not use an in-air simulator yet, but this is actually something that is ongoing currently in our project with Boeing. So they are now transitioning from the ground runway scenarios to a scenario that includes both an in-air approach as well as and then landing and then taxiing on the runway. So maybe in a year's time we'll have more to say on that. But in principle, yes, you can code up those sorts of scenarios in a language like Scenic. As Daniel mentioned, Scenic is agnostic to any particular application domain, right? So the core Scenic language basically has support for these abstract objects with geometric relationships between them, and for specifying these sorts of agent behaviors at an abstract level. But then you can write a library that specializes it for a particular domain, like maybe in-air scenarios. And then once you've written that library, you can use that in your Scenic program.
Cool, thanks.
So maybe we have time for one more question. If not, I would like to ask a couple of questions if Dana allows and Lou allow for a bit of extension. you have been focusing very much on falsification testing, and you still show that with this bricks about this coverage-based testing and the relation to the physical world, some steps also towards the other question, and that would be like, how would you prepare some kind of a case to the regulators to show that your autonomous vehicle is actually safe to go on the road, and how would you use the fact that you have the simulation to minimize the effort? So can you comment a bit on that, on how to prove that or get some confidence that it is working as it should?
Right. Okay. Excellent question. So, so I think let me just peel this question into two. Right. So the first is, how do you build an assurance case for regulators? I think this is basically a socio-technical problem. And recently, I've been on this committee of the World Economic Forum Safe Drive Initiative, which includes both technical and people, as well as people who are more policy side. And it's a complicated question, right? So we advised the World Economic Forum's group on a document that they published last November, which is basically lays out a sort of a best practices approach towards AV testing and certification. And one of the things I pushed very hard for is formal specification, right? So you want to be able to specify the scenario that the AV is executing. And then use the specification to be able to evaluate whether milestones have been met, right? So you have a set of scenarios coded up in a language like Scenic, and now that's as precise as you can get. So not natural language ideally, but you want it in a language like that, and then you use that to generate test cases and simulation and the road, and then have the AV evaluated against that. Now, the question is, how do you get it evaluated? And here, it really is up to the capacity of our tools, right? So I think, personally, I think in hardware verification, if you look to verifying microprocessors and other chips as a success story for formal methods, the workhorse of formal methods in the chip design industry is really simulation-based verification, right? Like, people like Dana Fisman have worked on this topic. And pushed ideas from formal methods into industry. And I think that's the workhorse, right? Like, so again, there, formal specification is key. You write the assertions, and then you do coverage-directed simulation to be able to find as many bugs as possible and meet certain coverage goals. So I think we are already seeing in the AV and the autonomy area tools like that starting to apply it in industry. So, so I think that could be a way to increase confidence for regulators, right? So that's one part of the question. The other part of the question is, for at least from a formal methods person, you really would like a proof, right? That goes beyond saying that I ran all these simulations and I found a bunch of counterexamples, and then I retrained and redesigned, and now I can't find any counterexamples. You want to be able to go beyond that. I think the key there is abstraction, right? So this is really coming down to this point. So abstraction and compositional analysis. We have to be able to come up with ways that we can create abstractions of these more complex components, prove properties about the abstractions compositionally, and then be able to monitor those abstractions at runtime. So it's really a combination of these three bullets that I have here on the slide, which is, apply abstraction, compositional reasoning, but also integrated with runtime assurance. That's my take on this, but obviously this is part of the reason why this is still very much an open area, right? So how do we give guarantees for these systems, stronger guarantees, right? I think that's still very much open.
Well, thank you very much again for this wonderful tutorial, and I give back I decided the organizer how to proceed because we have been quite late with the tutorial. So Dana Lu.